when they watch this on YouTube. So that's another thing that's happening. So these lectures are recorded in YouTube, just so that you know. Okay, so we'll be here having class Monday and Wednesday, not Tuesday and Friday, but just Monday and Wednesday from 3 to 5, and then Friday from 3 to 4, okay? And there's my email and all that sort of thing. The syllabus is online for those of you that are watching online. Okay, we're going to cover a few things. We're going to cover kinematics, which is how objects move, and then we're going to cover kinetics, which kind of gets into the reasons why they move. Okay, so that's what we'll be looking at. Now, to be in here, you should have had statics, because we use the forces and such that are used in statics. And then you should also, and that's basically the requirement. Plus also we do a fair amount of integration in here, so you want to have had calculus 2. Okay. And then it's good if you've had physics. You don't have to have had it. It's not a requirement, but that can be helpful in here. I just zapped my computer, so I'm going to have to start this over again. I'm sorry, I'm having a rough start here. I think it's right back there. That's still recording, even though I turned off. Huh. So I better have a look at that. All right. Okay, now for as far as that textbook goes, what you need is a packet of materials that has that picture shown on the left on it, okay? And that's available in the bookstore. If you're online, you still need that. Now, I do have some stuff I can hand out to you to keep you going for today, but you do want to go to the bookstore and get that. It's at least edition 2.00. Okay, is that the current edition on this thing? Yeah. Okay, great. So thanks. It's 2.00. So get that edition of I call it the packet. Okay, it's just a shrink wrap packet of notes. Now that's the book that you need, and so you want to get that and you want to bring it to class with you because it has the stuff that we cover in class in it. Okay. And you don't want to try and copy down everything I'm putting up on the screen. You want to use the book because it has a lot of the stuff I'm putting up on the screen in it. It also has homework on it. Okay, so the first 30-some pages are homework questions, and then the material after that starts on about a page 100 or 110, and it goes through the notes. The notes are numbered by 10, so they go 100, 110, 120, et cetera, and that way if I need to add pages in the future, I can. I'm always changing this thing around, so I've kind of anticipated that, so I number it kind of funny, but the numbers are sequential. I mean, if you start 120, it's always after 110. There might be some extra pages in between the two, but it's always sequential. The homework pages are just numbered 1, 2, 3, 4, 5, 6, 7, up to about 32 or 34 or something like that, okay? But so the important thing here is you really need to have those notes, okay? So be sure you get a copy of those. All right, now I would also suggest having a dynamics text, but you can get any dynamics text you want. I mean, this subject has not changed in 100 years. I mean, it is what it is, and so you can use any dynamics book you want. I don't care what it is or how old it is. It doesn't make any difference. But I do think you want something more in depth than just the notes. The notes just cover what we cover in class. An old textbook or any textbook will have more in-depth coverage and have more examples and things that you might need down the line, when you're referring back to something. Okay, so the notes are good for class, but the textbook goes more in depth and it's something you can refer back to also. Okay, so I would suggest getting that. And we have some in the bookstore, but you could use whatever text you like. It doesn't really matter which one you might get. All the homework's in the notes, so it's all self-contained. Yes?
The hard book in the bookstore can be bought on Amazon for if you buy the paperback, it's $100 cheaper.
Okay, and you could buy a 1984 edition too. It just doesn't make any difference. So yeah, right. So there's lots of ways to save money on books. I hope you're somewhat familiar with that. I know textbooks are awfully expensive. So just, is everybody okay with what I'm saying? Or just get the notes and bring them to class. That's really the main important thing to do. Okay, that's the important thing to do. Okay, now the grading works. Exams are 85%, homework is 15%. I use two systems to calculate your grade. One of them counts each of the 3 tests equally. The other counts the midterm more, or excuse me, the final exam more. The tests will add up to be 85% of your grade. The homework will be 15% regardless. Now what I do, I've got a spreadsheet. I enter all the stuff. It calculates your grade both ways. And then I got a little bit of a logic routine in there that compares the two, and it picks the higher of the two. Okay, so that's how that'll work. Now, being as I do that, the spreadsheet embedded in Moodle. Now what Moodle is our version of Canvas if you're from OSU. It's just a course management system where we list grades and put handouts and stuff like that. Moodle can't do this, okay? So what that means is the score, I use Moodle to put your scores in, so you got some idea what the scores are you got on the test and the homework, but I don't calculate the grade in Moodle, okay? Now Moodle will have a course total that comes in the program. I can't change that, but that's a meaningless number because I can't put these two formulas in there to calculate that, okay? So I use Moodle simply to tell you what your scores were. I don't use it to calculate your grade. So don't pay any attention to that course total. I'll remind you of that perhaps near the end of the term when you're looking maybe at your grade and all that, but just remember that, okay? That the course total doesn't really mean anything in Moodle. Okay. Okay, we're going to give you 3 exams and such as I'm saying in the top paragraph there. We also want you to prepare you for a professional work environment. So I expect you to show up in class. I expect you to participate in class activities, show respect for everybody in here. If there's any sort of issues where you're going to be out of class for a while or something comes up, just communicate with me and we'll figure out a good course of action. Okay, you got to be proactive on stuff like that though. You know, it can't just kind of roll along and then say something at the end of the term. If something's up, just talk to me and we'll figure out what, the good course of action, okay? So that's part of, what I would expect from you. Okay, we got the schedule there. We've got exams. The first midterm is approximately week 4. Second midterm is approximately week 8. I'll give you at least a week's notice for the midterms. I don't schedule them on an exact day. I'm not quite as structured in that as some engineering teachers are with everything scheduled out before the term starts. But I'll give you at least a week's notice on them, okay? And I'll assign homework and that'll be due usually 2 class periods out from when I assign it, okay? And the homework here, the final exam this is not correct here. The final exam is Monday, I think. Could you check the bottom of your syllabus? Is that what it says? The 11th of June? That's what I remember. June 11, and that's from 3 to 5. Okay. Now, the testing, for those of you online that are watching this, I'll work with you on the times with that. Quite often I'll have a test in the evening too for online students because I know they obviously they can't come at this time, so they probably can't make the tests either, but I'll work with the online students on that. I'll come up with an alternative testing time. But for those of you in class, here's the time for the final. Now, if you're dual enrolled at OSU and something's up, just tell me and we'll figure it out. Don't worry about it, okay? Because sometimes I know OSU has their finals all over the place, and that can create conflicts sometimes. If that's a problem, just talk to me. We'll figure it out, okay? Okay, on the back, I got a little bit about professionalism and what's expected of an employee. That's a good list for students too. What else do we got here? We've got disability services. If you have any sort of need any sort of accommodations, just talk to me and we'll figure them out and we'll work that out. Okay, so if there's anything up with that, just let me know and we'll make whatever accommodations we need. We've got an anti-discrimination statement here. That LBCC doesn't tolerate discrimination based on a very long list of different things there. I think what I observe here is we're all a little bit different and everyone's got a different background, so just treat people with respect regardless, and I think that'll be just fine, okay? So keep that in mind, that's a stated policy at LBCC. We also have an academic honesty policy. Work together on your homework, help each other out, but if you want to receive credit, do your own work, okay? Any cheating on homework or tests, I'll get you a 0 for whatever thing there was any cheating on. Students who aid other students who cheat will also be held responsible, okay? So don't ever like dealing with that, but when I have to, I do. So just be aware of that policy there, okay? If anything happens on a test and you get a 0 on a test, that makes it pretty much impossible to really pass the class. So just be aware of that, okay? So let's just not go there. All right. So we got any questions on that stuff? All right. Let's see, I got a homework format that I like people to use. Now, those of you that have me may not need one of those, but whoever wants one of these, I'll give them too. If you've not had me before in classes, probably want one of these just to see what's not supposed to be looking like. Anybody got one of those that wants one? All right, that should be available online under the downloads for those of you online. Now, the deal with this is, now, first off, in the packet, I've got a number of the homework problems that are written up for you already, and you just need to fill them in. The way the packet's organized is the homework's on pages 1, 2, 3, 4, 5, et cetera, but there's like a page, could you flip that page right there, please? This guy right there. Is there one right after it?
After this?
Yeah, there we go.
Yeah.
So you'll notice on page 2, there's a particular problem that's given with a bunch of other problems, but on 2A, I've got the thing written up for you with answer blanks on it, okay? So the idea there is maybe half the homework problems, they're already written up for you. But the ones that aren't should follow this format that I've got here. Now, I know this takes a lot of time, and I know time isn't something second-year engineering students usually got much of. So I try and help you out a little bit by writing some of them up. But you should be writing your own up too. And there's a number of reasons for this, right? I mean, we want this stuff organized because organization is kind of what we're about at engineering. That's one of the big things that we do here is get our work laid out nice and clean. It helps us to work through it in a good way. It helps other people to look at what you've done and figure out what the heck you've done. It looks professional, and that's just the expectation in the field, that you do your work that way. If you work for a consultant, you're going to get billed out at about $100 an hour probably out the gate. And people expect stuff for $100 an hour. They don't expect sloppy work. They expect work that looks professional and it looks like someone knew what they were doing when they did it. That gives the client a sense of comfort if the work you've done for them looks professional. It's what they expect. So just start working on that now, okay? Don't just say, oh yeah, I'll get to it later. Start on it now and try and get your work done quickly and make it look good, okay? Now, it doesn't have to be perfect. That's not my expectation, but it ought to look reasonable. And what I want here is your name, a date, problem number, and page number across the top. I want a problem statement. The reason is that makes it into one complete set of work. If someone looks at that piece of paper, they know what's going on. If you don't have a problem statement, they don't know what the heck you're trying to do, okay? So make sure they know what you're trying to do. Now, you don't need to be writing down the whole problem statement. Paraphrase it, it's fine, okay? So this problem statement might have been longer in the book, but I just made it find the forces at the supports. I got a simple line sketch with a straight edge. Don't photocopy, just start to learn how to make a decent sketch in a hurry, okay? Okay, so we got, forces, dimensions, reactions. We got the work clearly laid out where someone can follow it. We got all the answers in one box. Used a straight edge. I got an old library card I use. And notice the handwriting isn't the prettiest thing in the world, but it's big enough to be legible, okay? And start to figure this out. I mean, it works different in school in a lot of ways. If your 9 looks like a 4, in school you get a little red mark and a point taken off. But if you're doing work and, I'm a civil engineer, I do grade staking out in the field, man, I got a 9 and it looks like a 4. That ain't going to end well, okay? People are going to build something wrong and, that won't go well, okay? So just start to figure that out and start to do your work with that in mind. And just keep working at it, okay? A little bit at a time and get good at it because it'll pay off when you start working, okay? All right, so that's the expectation there for when you're doing work that isn't written up for you. If it's written up for you, just use the dang page, fill in the answers blanks, and off you go. That's fine, okay? But if it isn't, do it this way. Okay. So we got any questions with that? Okay. All right. I'll get you a formula sheet eventually here. Hopefully next time it'll look like that. It's on blue paper. This is you'll have this for working on homework and whatnot, and then you'll also have it on the test. So I'll give you a new copy of that, okay? So you get a formula sheet. Okay, a couple of things about the class. This is out of the OSU paper, the barometer from a lot of years ago. The question is, what have you learned this year at Oregon State University? And the student's answer was, showing up for class is pretty important. And it's pretty good advice, okay? So show up wherever you do it, electronically or in class or whatever, be here, okay? And not just don't come. I mean, start listening, get involved in what's going on. That's how you learn. You're paying us $400 to be here. Make it worth your while, okay? Okay, here's a headline out of the paper. This is quite a while ago, 20 years ago, I think. They had a little Mars rover and they crashed it into Mars. And the reason is the design team did their stuff in metric and the operations team thought they were doing it in English or vice versa. I can't remember. They screwed up the units. Nobody put the units on there. And they smashed the Mars rover into Mars. Broke it, didn't work. Okay, so use your units, carry them through. Be sure people can follow it. I'm sure you all were big Teen Beach movie fans. Okay, here's Mac. She's the smart one. Here's her boyfriend. I think his name's Brady, if I remember. My daughter watched this quite a lot, so I got to know more about this than I wish I did. But so Mac's the smart one, and she says, I can explain it to you, but I can't understand it for you, okay? That's what she tells her boyfriend. And, I think that's good advice. See, I'm teaching the class, I'm explaining it, but you got to understand it, okay? And those are completely different things, okay? You don't just listen to me and understand it. You got to do it, okay? You got to get involved. You got to do some of the work. You got to struggle with it a bit. That's how you learn it, okay? So, succeed here because these are important skills, okay? It's tough to shortcut this stuff in engineering school. This will serve you well when you get into pro school too. I mean, come to class, engage, pay attention, think. You got questions, ask them. You're paying me to answer your questions. Ask them, okay? Do your homework and do it independently, 100 times now I've seen errors on homework that go viral. The first person that did it made the error and I get 10 copies of the same error. Kind of see what's going on there. One person's doing the homework and 9 people are copying it. That don't help the 9 people. They don't know what the heck they're doing. They're just copying the same dang mistake over and over again. Okay, that's not good. All right. Okay, don't cram before a test. That doesn't work. I mean, it's not complicated. It doesn't work. Okay, we're just studying a little bit all the time. Stay up with it. You can't just shove all this stuff, especially not dynamics. I mean, this stuff really is rocket science, if you know what I mean, okay? You can't just, it just doesn't work. You can't get that much information in your head the night before the test. Find a good study group, okay? And I'm not just harping at you. These are proven, researched facts. This is how people learn, okay? This is how it's done. Do it if you want to succeed here, and if you want to succeed in engineering school. That's just how it is, okay? So we good with that? We got any questions on any of that? Okay. We got our engineering lab over here. People study over there sometimes in the back. They're always welcome in there. There's study groups over in the Learning Center. I don't know where else. There's Science Help Desk down in Madrone Hall. There's a couple study rooms over there. So find some people if you like working with other people and start help each other out. We're a little short of tutors for this. We have trouble with tutors because everybody graduates when they finish this class and goes on to OSU. I'll look into that, but I don't know if we've got any right now. Okay. All right. We got any questions on that stuff? All right. Well, let's have a look at some dynamics then. Spring. Intro. Yeah, I guess we'll start here. All right. Let's see. All right, so for those of you online on the downloads, I've got some of the notes. I don't have the full note packet online, but there's a PDF of the beginning pages of the notes you can download. You should get a copy of the notes from the bookstore too. You can order them and have them shipped if need be if you're from out of the area, but you should get some copies of these, okay? You really do need them for the class. Now, if you don't have them yet, just go to the downloads in Moodle, and there's some copies that you can use there that'll keep you going here for a few days. Okay. And let's see here. When do we do this? Okay, so for those of you online, obviously you've made it to Dynamics because that's where the link is. You can just subscribe to my channel too if you want. But this is something, for those of you in class, you can use this too if you want. Just go into Moodle, which again, it's just like Canvas. It's the same sort of thing. And here's Dynamics. And here's the homework due list. That'll have what's due at any particular time. So I add stuff to this as we work through the class. Here's some downloads. So there's the spring. There's the formula sheet, the homework format. Here's a little spreadsheet you can use to calculate your grade. You can kind of see where you're at. Here's Dynamics notes, pages 110 through 200. So those of you online, you can download those and follow along. Here's the homework, the first homework problems too. So, now that's not the whole thing, but it's enough to keep you going while you get the notes. Okay. All right, so there we go. I guess that's it. All right, file. All right, and so let's have a look here. All right, so this is in your notes. It's on page 110. And so this is a big reason why I make these things. Why should you be copying all this down by hand? What's the point? Why not just give it to you and there it is? This just saves us a lot of time, saves you a lot of screwing around and writing stuff down. So I gave you copies of stuff like this, okay? Okay, so dynamics. We're going to use the stuff you learned in statics, but then what we're going to do is we're going to have motion now. So we're going to analyze the forces like you did in statics, but now the sum of forces will not be zero. And I just lost my screen recorder, I think. Man, I'm having some problems here. Or have I? No, okay, I'm good. All right, I just got too many icons. All right, good enough. All right, kinematics analyzes how things move. Kinetics looks at what causes the motion. Okay, we'll start off dealing with a particle, which is like a point mass, like a pool ball or something like that we analyze. Then we'll get into objects that have dimensions and such. Okay, rectilinear generally means a straight line. It might mean like a parabolic sort of motion like you get with a trajectory too. Okay, displacement is a change in position, which is the final position vector minus the initial position vector. Those are designated by R. If you're talking about scalars, you use S. Now, distance is the total length traveled. It's different than displacement. So an example here is if you start at some point and then move over to the right one and then move up one. So let's say we're moving and we're driving somewhere. And so what we're going to do here, we're going to start here, we're going to go a mile east and then a mile north. All right. Now the displacement is 1 squared plus 1 squared and take a square root. It's 1.414. It's along that hypotenuse. The distance is 1 plus 1 and that equals 2. Okay? So that's the difference. Displacement is your final position minus your initial position, which is a straight line from one to the other. In this case, its length would be 1.414, whereas distance is how far you actually travel. If you're on a car, it's what would show up on your odometer. Okay, T is time, R and S are displacement, V and V are velocity, and A are acceleration. If you're typing, you specify a vector with boldface and a scalar without boldface. If you're just using drawing by hand, you put an arrow over like that to designate a vector. Okay. All right, now we've got some relationships between some of these things that we want to call out. Now what velocity is the change in displacement with respect to time. Okay, and we can do that with a derivative. Now we do an awful lot of derivatives with respect to time, so we've got a shorthand notation for it. We just put a dot. A dot means a derivative with respect to time. So a velocity vector is r dot, velocity scalar is s dot. Okay. Now those are instantaneous because they're based on calculus. We can also calculate average velocities too, which would be delta r or delta s over delta t. Okay, so velocity is a change in displacement with respect to time. Now, acceleration then is the change in velocity with respect to time. And that would be v dot. And acceleration is, let's look at a car. Velocity is what your speedometer says, maybe 40 miles per hour. If you step on the accelerator and speed up, that's acceleration. That throws you back into your seat, right? That would be positive acceleration. It's a change in velocity with respect to time. If you hit the brakes, that's a negative acceleration. Okay, so those are accelerations when your velocity changes. And quite often you feel acceleration. You're thrown back or forward or something like that. Okay, so that's acceleration. Now, acceleration is also the second derivative of position with respect to time, because velocity is the derivative of position with respect to time. Acceleration is the change in velocity with respect to time. So acceleration there is the second derivative of position with respect to time. Okay. Now notice you can call these v dot, or a second derivative is r dot dot. Okay. Real easy notation. Just put a dot over there. It means time derivative is what it means. Okay. All right, now those are the fundamental relationships, and there's kind of a chain that goes from displacement to velocity, velocity to acceleration, using time derivatives. We can also get a third relationship here. If we look at velocity as ds dt and acceleration as dv dt, what we can do is solve both of those for dt, the change in time. So the change in time is the change in displacement with respect to velocity. Using this relationship, the change in time is the change in velocity with respect to acceleration. We can equate those two things together and essentially cross multiply. And what we get then is VdV is AdS. So that's another relationship we can use to relate these things together. With this, we don't need to worry about the time. This one's independent of time. An example of this would be if you're dealing with a spring. If you've had physics, you might know about spring force is a function of displacement of the spring, the stretch or compression in the spring. You could figure out the acceleration based on this relationship without having to introduce time into the relationship. So that can be kind of handy, all right? All right with those? Okay. Now those are 3 calculus relationships. They're on the upper left-hand corner of your formula sheet. When I get that to you, you'll see those. Those are calculus relationships for instantaneous accelerations. Now, if acceleration is constant, now if I handed this stuff out to you in class, I didn't include this page because you don't really need it right at the moment, okay? It's in your book. If you got the book, you've got this 115. If you got what I handed out in class, you don't. Just look at one of these. We've got the acceleration as dv dt. Well, acceleration is constant, okay? So let's kind of work through this a little bit. Here's a common thing we do in dynamics. If acceleration is the change in velocity with respect to the change in time, the acceleration times the change in time will get you the change in velocity. Okay, that's an instantaneous relationship there. We're just rearranging the dv dt. Essentially, we're treating those differentials like they're algebraic variables. We're multiplying both sides of the equation by dt, essentially, there. Now, if that relationship holds in an instantaneous sort of relationship there, we can integrate it, which means to add it up over a given interval. If we integrate dv, we just get v. And the limits on that would be the initial velocity and the final. So that would end up being v minus v0. And then if we integrate ACT from 0 to t, we'll just get ACT is all we'll get. I mean, we don't really know the nature of AC. It's constant, it's just a number. So when we integrate it, it's just times time. And if we plug in our limits, we'll get ACT minus 0. So what we end up with then is the acceleration times time is the difference in velocities. We can solve for the final velocity and get that v0 plus ACT is v, the final velocity. Okay? And we can do a similar process with each of the calculus relationships and get to these 3 algebraic equations. Now those only hold when you got constant acceleration. That's the only time they'll actually hold. Okay? So if I've got instantaneous relationships, I'll use calculus. I'll use those 3 relationships. And if I've got constant acceleration, I'll use these. Okay? So here are the constant acceleration equations. Here are the variable acceleration equations. So just be sure you're using the right equations for the right situation. Okay? We agree with that? Okay. Well, why don't we look at an example here? Let's take a ball and throw it up at 22 meters per second. And we'll release it 1.8 meters above the ground. Let's see how high it's going to go and when it'll hit the ground. Okay. All right. So you all got this? This should be on 120. Okay. All right. So what's the velocity of the ball at point B? It'd be 0 because it's turning around, right? So it's going up and it's just about to come back down, and there's that one instant when it's 0. So at the very top of the flight, the velocity of the ball is 0. Okay. All right. Which way does acceleration act on this thing? It's down. Okay. So the acceleration's doing that. And what is the acceleration, do you suppose? Being as it's on Earth and it's affected by gravity. Yeah, 9.81, okay? And I'm having problems writing here, so you'll have to bear with me. I'll have to figure this little problem out, but for now I'll just do the best I can. So that's meters per second squared. Okay, that's the units on acceleration. Meters per second, which is a velocity per second, which is the time, so that's meters per second squared. And that's always down. All right. So if we want to know how high it'll go, we're going to have to look at some things. Now, first off, is that constant acceleration or variable? That's constant, right? Because that ain't going to change. You always have the acceleration due to gravity, and it's going to be down. It's going to be a constant acceleration. So if it's constant acceleration, I got three equations that I can use here, and there they are. All right. So I got to use one of those or some combination of them to figure out how high the ball will go. Okay, I've got my initial velocity, I know my acceleration, and I know the velocity at the peak there. Okay, so that's what I know. So this is 9.81 here. All right, so if we think about what we know and think about what we want to find out, hopefully we can get us an equation here that'll get that for us, okay? So it is released 1.8 meters above the ground. How high will the ball go? Okay, now we express that with S, right? I mean, that's our variable that we use for displacement. So we want to find S, and we know S0, we know V0, V final, and we know the acceleration. So is there any of these that's going to get that for us? Which equation would you use? Okay, now the second one's got time in there, doesn't it? And we don't know that yet. Now we could work through it and find it out, but there might be a more direct way to get to what we want. Yeah, this one here, eh? Okay, because we got the displacement. We want to find S. We got S0, we got A, and we got V. Okay, so I'd use that equation there, and I'd be conscientious about how I plug stuff into here. Okay. So there's my equation I'm going to use. And I know that VB is 0. So 0 squared is 22, which is V0 squared, plus 2 times AC. Now AC is negative, so you got to watch your signs on this stuff, okay? You got to be a little bit conscientious about how you approach this stuff. So watch your signs. Okay? So plus 2 times negative 9.81. Now the other thing on this is notice how we're defining height. Height is measured from point C to the top. Now we're already 1.8 meters up when we start. So given that definition of height, we need to say we've got S is what we want to find, and our initial S0 is 1.8, okay? So I'd go ahead and plug it in like that. So when you're doing these formulas here, you just got to be a little conscientious about how you approach them and how you plug stuff in. Okay, the first thing we figured out was its constant acceleration. And then we figured out some of these other things, that VB was 0. We knew what the constant acceleration was. We've got the initial height, but not the final. And we got the initial velocity. And then when we plug everything in, we got to get that acceleration as a negative. we got to realize that 1.8 is our initial height, okay? And that comes from the fact of how height is defined right there, okay? All right, are we doing all right with that? So that'll get us 26.5 meters. Okay. We're good. All right, what's the next thing we want to do? When will it hit the ground? Now, this is getting back to some of that stuff about word problems, right? When, which variable is when? Yeah, it's time. So t is what we're after. We got initial velocity. We got the height now. We got s, 0 and s final. We got the final velocity. We got the initial velocity. We got the acceleration. We got lots of stuff. So hopefully we can get this thing figured out. What's the most direct way to get this one? So we want to find t. Which equation would be the one to go with? Yeah, I think it's this one. Now, why isn't this one going to work? It looks easier to me. It's only got 3 things in it as opposed to 4. What's the velocity right here going to be?
Not 0.
Yeah, you can't assume that the velocity there is 0. That's not a good assumption because the velocity is 0. Why? Because the ground's there, right? It's going to hit the ground. Now, there is nothing in these equations that allows you to say the ground is here, okay? These equations just look at the constant acceleration, the displacement, and the time and the velocity. That's it. You can't tell that equation. It's not smart enough to know that it's going to hit the ground. Y'all understand kind of what I'm getting at there? What that equation does is it generates a parabola that goes up and comes back down, and it doesn't know anything about it hitting something or anything like that. So this doesn't work. The velocity, what you would use for this V right here would be the velocity just before it hits the ground, not on account of hitting the ground. So realize what the limits are of those equations. It doesn't know that there's the ground there. It doesn't know there's a wall or a bush or a bird flying overhead or anything like that, or the wind blowing or anything like that, okay? It's just a simple equation, and that's all it does. So we got to use the middle one. Okay, and just plug everything into that. Okay, you got S, you got S0, V0, T is an unknown. 1/2, of course, we got AC, and then we got T squared. And it's the same sort of thing here. Watch your assumptions, and the signs often can be a little problem on these. Be careful about what S is. This is the final displacement. S0 is the initial. And just be sure you're plugging in everything the way you ought to. Okay? So the final displacement is 0. The initial is 1.8. See, because we're seeing when are we about to hit the ground here. That's 0 displacement. We're starting 1.8 meters above that. And then we got V0 times the time. Then we got 1/2 times the acceleration. That's got to have a negative on it because it's accelerating down, and then T squared. And then we just go through the whole quadratic equation stuff, okay?
Shouldn't your 22 be negative out in front?
No, it's the velocity's up, so we're good on that, we're calling up positive. The acceleration's negative, and the 22 is positive there. Because it's the velocity's up.
Yeah. But in the equation, it should be a negative. It's the negative of the second integer, or of the second. Sorry.
Oh, you mean in the quadratic, right?
Yeah.
Oh, right. Okay. Yeah, I've got it. Let's see. Negative b squared. So that negative been out front. Is that what?
Yeah.
Okay. That's.
Yeah. Acceleration positive, so I think you just have down.
Oh, did I got like? Oh, yeah, all right. See what I did here, what did I do? I got this, I just solved it directly there. And then it looks like I multiplied through by -1 here. So then it's what, b squared, that's negative b. So that turned it into positive here. See, I multiplied through by -1 because I like that lead coefficient to be positive. It doesn't have to be, but that's what I did. I don't even know why I did that, but I kind of like that lead coefficient positive.
Right.
So
Where all these
there we go. Yeah, it came out in the wash. Okay, I see what you're saying. Because that's a negative b, which is negative of -22, the way I've got it set up.
Yeah. All right.
Okay. And then we just plugged it into the quadratic equation. Okay. Okay. You doing all right with that? All right, so we get two roots out of that like you do out of quadratics, -0.08 and 4.57. So which one's the answer? Yeah, it's this one. What's the significance of -0.08? What's going on with that? Yeah, right. See, this thing is, again, it's just a parabola. That's all that equation's doing. It's coming up with a parabola, and the parabola is infinite. I mean, it goes down here, see? And what we're asking this equation is, when does the value of the parabola equal that line right there? And it's telling us both answers. Now, it doesn't know that we start at time 0. It doesn't care, all right? So it gives us both answers. That's all, okay? All right, so any questions on that business? That's a little start there with constant acceleration. You might have seen some of that in physics if you've had physics. So when I'm doing this stuff, I identify its constant acceleration. If it's constant acceleration, I got 3 choices, okay? I don't sit there and scratch my head so much. I just say, okay, I got to use one of these or some combination of them. What am I going to use to get what I want? That's how I think about it. There's not unlimited possibilities. There's 3. So figure out the one or the combination of them that's going to get you what you want. All right. All right, how about the last one? How fast will it be going when it hits the ground? What do you think on that one? We're just after velocity. We found the time there somehow. Did we find the time, or how the heck do we do that? Oh, right here. Okay, we got the time. Can we get away with that one? That's the easy one. I might be able to, I think. I mean,
Well, the time also includes it going up, doesn't it?
yeah, which is fine. This will just do that. It'll take that, it'll account for that. It'll follow that parabola and get the time to travel the parabolic path as long as we input the right stuff into it. So what we're doing there, and see, we've got, if we run it that way, we know that the initial velocity is up at +22 and the acceleration's down. So it'll get us the velocity, and notice the sign on there, it's negative. So it'll figure that out for us, okay? Because we've got a parabolic path with a negative acceleration, and we want to know what's the velocity at 4.57. And this will get us the proper sign. It's coming down. Okay? So that'll all work out. So not only does it give us the magnitude of velocity, it also tells us the direction with the sign. Okay. We got any questions on that? You do all right? Good.